Bang. Ooh, it's going. Hi. All right. This is just hopefully a fairly quick video on how to deal with cars that are driving. This example is straight out of the whiteboard, but on a hill, on a banked curve, they'll call it. So usually the first thing they'll tell you to do is what is the speed that this guy could, the phrase I use is let go and let physics take the wheel, and still go in a nice, happy, flat circle so that he doesn't drift up, doesn't drift down, but just let the road itself push you in the circle. So if you're going at just the right speed, you won't drift up, you won't drift down. They call that lateral, so there'll be no lateral friction whatsoever. The way you do that is you just add up the forces, sum the forces. Someone should make a law. Acting on this car right now, there's only two real forces. There's gravity, that shouldn't be too tough, and then the road itself is exerting a normal, which I call the Fn. Please remember, normals are always perpendicular to the surface, okay? Now you guys are used to breaking down gravity into parallel and perpendicular. We're not going to use those components for this one though, because we're going to sum forces in x's and y's, but I dotted them in there so it will help you visualize the angle that we're going to use. Where you used to say, you're used to saying that if that's theta, well then gosh, that angle is theta also. And the reason I drew that dotted line there is so hopefully you can tell that the normal red with the dotted green there, the perpendicular, makes an X with the gravity and the normal that is in the Y right there. So those two angles then are the same. So if that's theta, that's theta. So that's the only reason I drew those dotted lines there, just for reference purposes. So the direction then that is towards the center of the circle is over here somewhere. So there's your FC is going to be pointing that way, or whatever centripetal force there is. Right now there's only one centripetal arrow, and that's that one. And so that'll be easy to sum that force to equal an mv squared over r. So what I will do is we can start with the x or start with the y. I usually start with the y because we'll put a y into the x. So if we sum the forces in the y, there are only two. There's the Fn cos theta and the Fg, which I didn't label, sorry, but that's pretty much gravity. So upwards is positive. I have an Fn cos theta. From that I will subtract Fg, and that will equal the number of friends I have. So then I will put Fn is clearly, Fn cos theta, sorry. Cos theta is Fg, which you all know how to spell Fg as mg. And so if I were to want to know what that Fn is, I would just push the divide button. It is mg over the cos of theta. That's what that red arrow is, that the road itself is exerting on the car perpendicular to the motion. Now, if they don't give you masses, g's, thetas, whatever, you have an expression for the Fn, and that is what we are going to end up using, putting it into the sum of the forces in the x. Okay? Summing the forces in the x, again, you can tell there is only one x arrow, and that's that one way up top in red, so that should be pretty easy. It is the Fn sine theta. That equals the centripetal force, because that's the only arrow pointing towards the center, and centripetal force, you know, is mv squared over r. Alright, and so then what we will do is say, alright, you all now see a swapper tuna T for that Fn. And so what I can do is put the Fn expression right there. So that'll be an mg over cos theta. I gotta then multiply that by the sine of theta, and that will equal the centripetal force formula, mv squared over r. Alrighty. Alright, and now you can tell a sine divided by a cosine will help us work on our tan. And it doesn't matter if this is a larger kind of van or truck or a small little motorcycle, doesn't matter. We get to kill the masses So this is G tan theta is equal to V squared over R. So if we were to then calculate, again, the ideal speed that that car could just go around the curve there, let go, let physics take the wheel, I would just multiply that R over, and so it would be GR tan theta is equal to the V squared, and so we simply square root both sides, and this follows that pattern that we said before. Anytime you're calculating speeds of things in circles, chances are it's some version of GR, and GR tan theta square rooted is the ideal speed that you could just let go and let physics take the wheel. So what did I do here? I guess I didn't give you any numbers, did I? Oh gosh. I said this is 12, so if that's theta, fine, and I don't know, let's call a radius 50, something about yay, what do you say? And let's just for giggles, let's give you a mass of something. Sometimes they'll do that just to give you a mass, and I think that's all we need for this guy, GR tan theta, right? So square root G 9.8 times the radius 50 times tan 12, bang, whoa, 10.2, duh. No, all right, so 10.2 meters per second is not how fast that car is going, but that is, again, just the ideal speed that any car could go and let go, let physics take the wheel, and just take that curve doing whatever by letting go. So then usually the problem will say calculate the force of friction or calculate the something or other if the car is going. So they may give you a velocity. Could be bigger than 10, could be smaller than 10, I don't know, it doesn't matter. So if they give you a velocity, you just it's whatever it is. If for example, which that clearly says example, the velocity is 20 meters per second, then in that situation, you're going too fast for the ideal conditions. You would instinctively let go or let off of the accelerator. You'll instinctively turn the wheel to go down the incline a little bit, but friction then will try to prevent you from sliding up the hill, which means friction will act down the incline. And so if you're going too fast, then I will add arrows to this drawing. So these arrows I'm going to draw now are only accurate if you're going greater than 10.2. So the direction friction would act, again, is along the incline. It is parallel to the surface. That's fur. But that force of friction is not acting centripetally. It's acting parallel to the incline. Centripetal would be towards the center of the circle, which would be there. So I will do the same thing I did with that normal. I'll turn it into a centripetal one that points towards the center, which is easy enough. I'll just do yay and tail to tip to that. Yay. What do you say? Yay. Now, can you tell that the flat surface here that I referenced theta to is parallel to that green arrow there? And if I extend these long enough, they'll intersect. So this force of friction is simply bisecting two parallel lines. So if that's theta, that means that is theta also. So the component that is helping me go in a circle is adjacent. So this is going to be a fur cos theta. And friction is also helping me, helping pull me downwards, keeping me on the hill. So this is going to be a fur sin theta. Okay? There is nothing going this direction, all right? Even though you are drifting uphill, friction is trying to prevent that. So do not draw an arrow outwards. There isn't one. Friction is trying to pull you downwards. So these then are the forces that we add up in the X and in the Y. So there's 2 X rows, there are 3 Y rows. So I will come over here and I will start with the Y. The forces in the Y equals May. May will once again go away. And there's 1 up, 2 down. The up is that normal component that is vertical, Fn cos theta. And then the two that are down are gravity itself, Fg, that's easy, and then the vertical component of friction, which we said is FFR sine theta. All of that adds up to, again, how many friends I have. So what that is was just to show you again, there's the Fn cos theta, that's the one positive, then I subtracted gravity, then I subtracted that particular arrow from it. So there's the y's. The x's, they add together. They're both pointing towards the center. So normal sine theta, same as it was in the previous example, and friction cos theta. So this will be sum of the forces in the x equals max. In this x example, x is towards the center, so that's a centripetal, which means that's a centripetal. There are two forces that we said acting towards the center. They're both going to be positive. So this was an Fn sine theta, so the normal component pointing towards the center. To that I will add the friction, again, which was, what, FFR cos theta? FFR cos theta. Those two will add together to equal the same thing it equals over there. The centripetal force is always mv squared over r. mv squared over r. Hey? Hey? Same thing. So then again, what we'll normally do, or usually do, is use that Fn as a swappertunity. We will put a y quantity into an x because the x is the one that has the mv squared over r term in it. So this is where different questions are created differently. They're not all equal, they're similar. So maybe they'll give you an Fn, maybe they'll give you an Fg, maybe they'll ask for a friction, maybe they won't ask for friction, maybe they'll ask for a mu, and if that's the case, just break the FFR into a mu Fn in both cases and do the substitution accordingly. So that's that. Now, if we're driving too slowly, if the velocity given was, say, less than 10, then you are going to slide down that incline, and friction will try to prevent sliding, so it will pull you back upwards. And so what that means is if, for example, I don't know, you're driving 5 meters per second, I have no idea, but I just wanted to pick one less than 10, that changes this direction of friction. Everything else stays exactly the same, so all I will do is erase that part of friction, which means that and that going to. Okay, so all that is done. So now if we are, again, going too slowly, the car will naturally drift downward. That component of gravity will drift us downward. So friction will try to prevent that from happening. So now I'm going to just draw friction that way. Okay, again, that ain't centripetal. So, to turn it into a centripetal, or at least x component, I will simply do that and this. So this hypotenuse, again, there's your friction. This now, hopefully you can, all right, you can tell what angle is theta, right? Because that was the horizontal surface that we referenced the hillside from. This, again, is purposely drawn horizontal, and that's parallel to the hill. So that is the same angle as the incline. So the x component of friction now is FFR cos theta. We're adjacent. The y component here is FFR sine theta, which is the vertical pointing upwards. And so now, when we sum the forces in the x's and the y's, please realize now the x's are not working together. They're fighting each other. So instead of adding them, I'll subtract them. And then I have two vertical y's, or two positive vertical y's, one negative y. So now I have two up, one down. Okay? So what I will do is start with the y, I suppose. It will be this plus this minus that. All right, so Fn cos theta, friction sine theta, minus Fg, which I can put over here. So it'll be Fn cos theta plus friction sine theta minus Fg is what war is good for. All right, so there's the y's. The x's will be the two that are fighting each other. Towards the center is positive, so some of the forces in the x, which I didn't write, some of the forces in the y, sorry, is max, which is centripetal, The positive one towards the center is Fn sine theta. Friction now is fighting you going in a circle, which now is FFR cos theta. That then equals mb squared over r. And again, that normal is usually what you'll use to swap statusify. So you'll get an expression in the y, put it in the x, and kill like terms and do all sorts of algebra. So from there, it's pretty much an algebraic nightmare. Again, it just depends if they give you that. If they don't, if they want, you could break it into a mu, or I'm sorry, not friction, this one here. You could break into a mu Fn, and in which case you'd factor out an Fn to get a swap substitution that is available. So here you could also call it a mu Fn. It just depends on what they give you. I don't know, but when you have cars going on bank curves, then again, just remember it's towards the center. That doesn't mean down the incline or up the incline. It just means a flat horizontal circle towards the center, wherever it's going. Figure out what the ideal velocity is. You know, you let go, let physics take the wheel. Boom, it's that. See what the question says, if it's a greater number than that or a smaller number than that, and then add friction, either helping or hurting you. And I don't recommend letting go of the steering wheel, by the way. I trust physics, but not that much.